Let's start the video. All right, about to do another Modal Logic video, and Bungus is probably a world expert on Modal Logic because she just hears so much of it. She probably knows everything about it. Okay, so let's start off with the video of what I'm sharing. Um, Modal Logic. Uh, where's my pen? Yeah. Modal Logic is like an extension of doing like regular predicate logic. In that if you have like there exists, it's basically like an OR operator over everything in the set, right? So like there exists some value X where some predicate holds. And for all is like a similar thing, where it's and over everything. So it's true if this is true and this is true and this is true, and all of those have to be anded together for it to be true. But one of the things that regular logic doesn't do well is it's not so good with handling facts that change. So like if you say it is raining, it matters like what day it is when you say that, right? It's if you say is it raining on Wednesday, you could have a whole bunch of facts that are all qualified by things to where you can't tell like technically whether they're connected together, but symbolically, like or, um, but with symbolic logic, they got a different way where they have a finite state machine and here it's like a machine A, and it's like a model of time where it can randomly change from state to state, setting variables as it goes, right? So it's here, and then when it goes here, it says that P equals false, right? And P equals true was what it was when it started. Um, and it can go just keep going through the state machine until it like finds um, something that you're looking for, right? And say here it happens to be the first place where Q equals true, right? Um, so when you make a statement about something, P and Q, um, you could say, starting from here, is it always the case that P implies Q? Is it always true at every state that you can reach starting from here, right? And can we find a place where P actually exists? And if P actually exists, and we can always find where P implies Q is always true, then that's like the whole basis for doing modal state machines. So let us go to the next page. And what I'm doing is I'm combining different logics that are they're typically like completely separate things. Like CSP is a logic that kind of comes from a paper by Tony Hoare, and it's like communicating sequential processes. And what that means is you just have a bunch of processes that are assigning valuables to variables and going from state to state. And they're communicating because they have queues in between them that are very much like Go queues, where you write into a channel, and if the other side is there to receive the message, it will get the message. And if it's not there to receive the message, then it's going to block until somebody's there to receive it, right? So you have process here and a process here. They're basically Markov chains, but there's places where someone on this side is listening for listening on channel. So the channel, and he's listening for a value that gets written into X. And on the other side, you have on this channel, uh, well, on a channel, well, you're doing the send from here. So you're doing the send from here. So on the channel, you're sending a value like say 6 on the channel. And on the receiving end, you got channel. You have a channel receiving, and then writing into the variable X. So what will happen here is you'll end up getting an X equals 6, right? So that is from CSP. trauma slash spin does this. You can emulate this in P and TLA plus. All those tools basically do some amount of it. Prism is the closest to what I'm doing, but Prism's got issues that drive me crazy. Crazy enough to actually make me want to just like write my own formal methods tool instead. Because like the syntax and the UI versus the CLI are different, so it's hard to automate things. And when I try to emulate message passing, I totally get stuck and I can't go any further. So even though it in theory does all these things, it's kind of hard. So CSP and CTL and LTL are different ways of doing temporal logic. And of course, temporal logic only works when you have a world to refer to. If you say something's going to happen in the future, you need a model of the world that progresses into the future. And the valuations on the variables will change as you move through time into the world. And in order to actually be able to model business problems, it blows my mind that TLA plus doesn't support it. P yeah, none of the tools other than Prism actually seem to support probability. And if Prism were just a little better, I would just use Prism. But you don't want communicating state machine, you want communicating Markov chains. And the reason why you want communicating Markov chain is if you want to model like real business processes, like things get queued up, you make a bunch of bread and the bread gets queued up on the racks. And because of the way that it queues up, you can calculate that the bread won't be ready for like another 4 hours, right? So you can ask questions like, if the bread making team gets in at 5 in the morning, well, what's the probability that by the time my store opens at 11, I have a delivery in probably. Um, so, so that's like what CTL and LTL give you the temporal logic. You add in probabilities, so you get Markov chains. And a Markov chain sending each other messages. That's how you have like a separate bakery machine versus a truck machine versus a storefront machine, customer's machine. And the idea you can ask questions like, will I get bread by 12? Right. And then you can ask things like, how much bread do I waste every day by not selling it? And that depends on customer behavior, whatnot. Okay. So the big idea is that you can use finite state machines to model this. You have a little less power than if you were to use a grammar, for instance. Like if you don't use a grammar, you kind of like have to manually track like open parenthesis happens twice, and then it forces you to have two closed parentheses on going out. Right? It has a more characteristics of like a programming language, like parentheses balance and things like that. But if you only have a state machine, that's actually pretty common for this kind of work because you're trying to do proofs where you want to model the world by generating a state machine that represents a problem, and then ask state machine like questions like, how much money do I think, what's the likely amount of money that I make today, right? And that all depends on the bakery generating the bread being delivered to the storefront, and then people buying what it is we actually made. And there's going to be mismatches between what we bought and what the customers came in to actually buy. That means there's going to be leftover bread at the end of the day. And when you add it all up, you can like figure out like how much did we make that day, right? We sold a bunch of bread, but then we paid a bunch of salaries to do all this stuff, and this is how much we actually made for the day. Um, so, and that's why it's important to have these probabilities here. Everything going out of a state needs to sum to 1, right? So this is 0.1, 0.1, 0.5, so 5, 6, 7, 0.3, so 5, 6, 7, 8, 9, 10, right? So that's like a constraint, for all these outgoing edges. They all sum up to 1. It's more like a for loop. In any case, probabilities equals 1.0, and is represented by summing all those things together. And this is like the main thing that I dislike about TLA plus. Not only does it think about it, it seems like they're totally hostile to the idea of even having probabilities. It's good that you can do safety and liveness without the probabilities, but you can't even start doing normal business problems without it. which kind of limits the usefulness of it, unfortunately. So, yeah, combining modes. This is where I ran into a problem where I'm reading about modal logic, and the biggest problem you run into is the books that you read about modal logic want to talk about possibility and necessity, where something is possible, where something is necessary, and something that is necessary means that no matter where you go from this point in the world, it's always going to be true forever. Um, because it's something that's like it has to be true. Like if you say 1 + 1, the answer is always going to be 2. There's not going to be like some state of the world where 1 + 1 is equal to a different value. So, and then possibly means that we've discovered a place where you can reach this. So it is possible because we found it in the state machine, and we can show you where it's at if we do a search for it. So what that means is when you're using CTL, you're taking a state machine and you're using it. And here's where the state machine's being used. And you can use the state machine to find a proposition that we're looking for. And it ends up being true at some spot. But then if you keep walking further, it may end up being false again. That is something that is possibly true. And in CTL, it's EF. Basically, it's like a shorthand for there exists. I'm sorry, it's like there exists and diamond, and it's a temporal diamond. And eventually is almost the same thing, except it's not optional. Something that is eventual will happen. Right? Like eventually, if you fly a plane around forever, you will eventually run out of fuel. Right? And that's kind of similar, except it happens to be for all tasks that you do. There will be a diamond. It's a temporal diamond, and that's AF. So eventually and possibility are two different kinds of diamonds in modal logic. And I was trying for the longest time to figure out how to combine the two logics into one. And of course, the solution was that eventually and always are like the normal modalities for temporal logic. But if you reinterpret what possibly means in such a way that it's a temporal version of possible, which means like from this state in the future, you will reach that. Then you have a situation where they both reach AG. And that's a wonderful thing because now I have a way to combine for all in there exists with either F for in the future or G is globally. So I have 4 combinations. But what was a little weird about it is like I got confused for the longest time. Like how can I can see how EF in CTL is the dual of AG, and that basically means that like the dual of it would be like you do a knot of AG with a knot on the proposition that goes inside of it, right? So these are opposites. But how can they both be AG if they're opposites? Well, what I discovered eventually was you only take the opposite of this operator and not the thing around it. So you got AF is a dual to AG. But the thing that's tricky about it, this is an LTL dual, and this is a CTL dual. And hooray, I can basically do a relatively general modal logic. I would like to do them all. I would like to be able to do belief-based ones, right? Like if I see a turn signal, then I believe that someone's going to turn versus I know whether someone's going to turn. Or even things like ought to allow and is permissible, they're usually done in terms of ethics. But for permission systems, that's exactly what it is. So I do see a way forward at some point to combine all the modal logics together, but the thing is I have to use a temporal definition of what they are, which means it's not really the crypty stuff. I've got my doubts about the crypty logic because there isn't like an automated tool. I think I have good reasons to have doubts about it. So if we zoom in a bit and show the one modality in CTL that we didn't use, EG, which means that there exists a path where something is globally true. And if you think about it, it's like you keep going down this path Um, and you can always avoid a place where it's not true. And that basically means you can fly a plane in such a way that you remain alive. There are ways to fly a plane where you're not alive at some point, right? So that's what this EG means. It means a way to always have the property that you're looking for exists, but there are things that you can do for that to not be true. So it's kind of like avoidably eventually, like eventually means it definitely has to happen. But if it's avoidably, I actually want to call it can always, right? So if you can always do the thing, then you've got a proof that says that yes, there is a way to fly the plane safely and land alive, right? Um, but that also means that there are ways that you should not be doing, and we need a plan for those things. Like there, it's possible to crash, but it's not inevitable. So one of the most confusing things about modal logic, um, the first book I got on, I couldn't make heads or tails of it for a long time because it seemed like people were just like making up random state machines. They didn't like start with like a sentence that they were parsing, so I couldn't figure out like um, where the states that they had were justified, where they came from, and how the links between states were actually created. But in temporal logic, this is a really straightforward thing. What you do is you say that a state is like just like a collection of valuations of variables, like the x and y. And when x and y are both zero, you're in this state. And when x is one and y is zero, you're in that state. And you get to it by assigning, x is now the value of x plus one, right? So you go from one state to another by making variable assignments. And this was kind of like the key to being able to mix modalities together. To say, hey, if I treat everything as a sort of temporal logic, where if I have a proposition that it's false in this world, and then I assign it to be true in the other world, it all works as long as it's like a time step. It might be an infinitely small time step, but it is a time step into the future. And so if you interpret it that way, then you can combine all the boxes and diamonds however you like. It's just, that's the good thing about it. Like say I start in this state x equals zero, and if I assign x equal to one, I go from s0 I'm in s1 now. But if I assign y equals one, I'm in s2 here, and maybe this would be s3. But in any case, you're moving through a state machine. Um, and that's good enough to like track the state machine that backs up all your temporal logic statements, because you're going to ask a question. You're going to say, is it eventually possible that x is equal to 7? And what it'll do is it'll find a state where it does x equal to x plus 1, and it shows that you can keep going through that state until it reaches 7. So the answer would be true. Right? Yeah. And one of the things is, since these are Markov chains that pass each other messages, you can have complex behaviors where, for instance, a bakery, you can show it like making bread and then dropping bread into the queue for the truck, into the channel for the truck. And the bakery doesn't really know what happens with it. It's the truck that does. So the truck comes by and it pulls breads out of the queue, and then it does a state transition to drive to the storefront. And then when it arrives at the storefront, it dumps off all the bread into the storefront through its channel. And then when customers arrive, customers end up getting bread because they show up with cash and they exchange the cash for bread. And so if you ask a question, can a customer get a loaf of bread by 1 o'clock? The answer is true, right? Things like that. Okay. So the real reason I'm designing this is for doing software development. And when you're doing software development, you can think of it as you just got a bunch of variables and you're assigning values of variables, and you go into different states when you do that. But the thing is, as long as you have a really close record of when you like increment a value or put a set of value equal to 5, or if you have to pause for a moment and send a value to a different process that you block and wait for it to receive that value, or if there is buffering in that channel, then you can just keep sending messages until it's full, and then you have to block and wait, right? As long as the message queues never get full, you're just dropping messages, and then you go on and keep doing what you're doing. But what I was doing was I would use a large language model, And in the large language model, I would say, hey, I need you to parse this news article. And I would give it like a random news article. And the news article was something about ceasefire. So there's a war going on, and there's a proposal for a ceasefire. And a large language model has determined that what you do is you wait for a violation. If there's a violation, then the ceasefire is off. And then they have to like do something to get the ceasefire back. And then when they're back in ceasefire, food deliveries happen, or bombs stop dropping. All like really optimistic ideas about what happens when there's a ceasefire. But what it generated makes sense. And what it did was, in addition to a README, which I might have an LLM keep up to date so that I know like what my source code project looks like, I would have a requirements LLM. And the point of requirements LLM is so that you always have an updated machine processable set of requirements. And so that if you say this thing implements multi-paxos, you can actually like have a model of multi-paxos and like say this is how it gets represented. And if you were to put things into the log file, you could verify, yes, this thing is behaving like multi-paxos, because like we look at the logs and it shows all these state transitions. And yes, it does in fact implement multi-paxos, and it looks like there's things like that. The other thing is if you include probabilities, which is like the whole reason you can't like just use TLA plus. If you include the probabilities and you have message passing, then you can model the business problems, but you can model them to a level of detail where if you just want to ask a question like, hey, I had this Markov chain, it kind of looks like like a like a queue. Tell me what the average length of the queue is. It should be able to just, yes, the average length of the queue is like 2.5, right? Um, and and if you ask like, I want a diagram of the state machine, you could ask it to just like draw a diagram of the current state machine. And maybe you look at the state machine and say, oh, that's too large. I want to collapse everything where, where y has the same value. Like if y is equal to 2, just show me a state machine that like groups a bunch of states together to be like one big super state. So you should be able to like get smaller subgraphs of how the system works by asking it questions. And the temporal logic is in there for mostly for like safety and liveness. If you want to prove that something actually happens, something good actually happens, you can say, hey, periodically somebody gets a little bread, and periodically we make money. And then you want to do proofs like we make more money than we spend, right? So the idea is when you're not running like a business that like loses money, or you want to do things like all of the loads that are not sold are given to charity, and that's like good for like business optics. You get tax breaks for helping the poor, stuff like that. So even though you're trying to minimize waste, you may tolerate or even require some amount of waste, so that like the bread that's not the highest quality stuff that you would buy from the store. Maybe it's like 2 or 3 days old. It's enough that like somebody poor like really wants it and really glad to have it, right? So there's stuff like that. So businesses. But the main thing is I was generating a markdown file that had Python code fences in it, where the Python code fences define the state machine, not necessarily finite state machine, but it's a state machine, and it's literally in Python. And the idea is you want to like run the markdown file as Python by extracting all the Python fences and combining them if it's not only one Python fence. But this is like the whole state for what I'm doing. It's the requirements in the markdown that came from the LLM conversation. And that's really important. So like everything I've said to the LLM, it showed up in here. And then when it generated a Python model, I've got the Python model. And when I've got a Python model, I get a PNG of the state machine. I might want interaction diagrams of, like I want to see the interactions between like the bakery and the truck, that's like, these are basically UML diagrams. So it's like state machine interaction diagrams. But the idea is they are highly interrelated, interrelated to the point that they're not really different, because if you see like a UML interaction diagram where one thing sends a message to another, what it is hidden from you is all the finite state machine state changes as it like goes down the timeline. It goes down the timeline and then suddenly have a bread go from the bakery to the truck. Well, what it hid was all of the queuing and uh, making bread, and it shows that like in order to get a loaf of rye bread, you have to wait like 2 hours for that to happen, for instance, right? So all this stuff gets hidden in the interaction diagram, and the interaction diagram is basically like some showing something that is possible. You're hiding the state machine that did it. You're hiding a bunch of the message sends. It's just showing you like a message send that is actually possible. It's typically what it is. Um, but the idea is if you have message passing Markov change, then all of these different things are implicitly there, and you should be able to ask for a diagram of them. And when you do a diagram, you should have a proof that it's actually possible by showing a temporal logic. Um, all of the formal method systems I was looking at, P kind of looks like Promula and Spin, in that you model a bunch of processes, and when you model the processes, you can like generate logic statements against it later. Um, P is a little less mathematical. It's the idea is you just write it like it's code, and then you have another process that also looks like just code, and they didn't like kind of go overboard with mathematics. With TLA, they totally go overboard with mathematics. Uh, they make an assumption that everybody wants to do computer science, and they will tolerate like having to read a whole bunch of math books to figure out how to model a business problem. I think that's total nonsense. So where I'm going is I have this GitHub repo. The main thing that's wrong with what's in this GitHub repo is I didn't think enough about having multiple state machines. And because I didn't think enough about multiple state machines, passing messages between state machines was a bit of a problem. So what I really, really want is, I guess I'll just write it out here. It has to be Markov chains that send messages. It's like the most important property, and the state machine is based on assigning variable values. Right? And what that allows us to do is to get around the problem of like, how do you justify these possible worlds that you're going to have? Well, a world, you get into another world when you make an assignment, and you get into a new state that you haven't been in before, right? So all these states are all the states that got created by assigning variables where the set of variables that are in there are unique, right? So like, um, if you tell the system, hey, there's a bakery and there's a truck and all these other things, what you're doing, you're defining finite state machine for one object. So it's the bakery, and the truck, it's like, truck parked outside the bakery, and then the truck driving to the store, right? And then you'll have the actual store itself, which is another finite state machine where stuff arrives, and I have to label them and put them on the shelves. There's some probabilities for certain things happening, so I could be in different state depending on how those probabilities went, and then cashing out doing it at the end of the day. And then customers come in, and customers, there's many different types of customers. Some of them appear to be like running their own sandwich shops and buying our breads to do it, and others are just like individual. And you got people that come in to buy a loaf of bread because they have a bunch of quarters that they want to turn into dollars. I see a lot of that. But in case you have the interaction between all these, and because they're all changing variables, then you can use the variables to make temporal logic assignments, to basically say that every day we make a little more money than we lose, right? And if we find a day where we lose more money than we make, then obviously that would be something that should like show up in our logs. But in any case, multiple machines and machines that have channels in between them, and so we have to pass messages, right? So when I get to the end of the truck coming in, it has to talk to something in the bakery, and then there's interaction between customers and the bakery. Like in one place, customers send a message to the store, or the store sends a message to a customer. But that's why you want communicating Markov chains. Super important. Anyways, Bungus is tired. I think we're done for the day. This is a second recording. Hopefully, the audio wasn't awful like it was in the last video. All right, bye. End this conversation and write the video out.